Okay, in part two, we'll be using NumPy and NumPy's matplotlib, library to demonstrate linear regression. So linear regression is a fundamental topic in machine learning which we covered in week 1, and we used it to demonstrate overfitting and underfitting using polynomial curve fitting on the data points. So here I plotted 10 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and they're randomly generated. And in a little while, we'll be able to see how to randomly generate this and how to plot this, right? So normally speaking, if you want to plot something, you would import matplotlib, so .py plot as plt, and then you can plot something like 2, for example, and it doesn't plot anything, it doesn't show up, right? The reason being we're now in a terminal mode. Our IPython terminal, IPython notebook is like IPython terminal, so it's not the same as if you run this as a piece of code. If you run this as a piece of code, it will show up a line, just like the perceptron demo that I released, right? Which uses this matplotlib. And matplotlib is like NumPy, kind of transferring some MATLAB libraries or frameworks into Python. So it got a lot of MATLAB style stuff going on, which is not necessarily the very nice package, but that's the kind of standard tool that comes along with NumPy, so we'll have to use it. Okay, now the workaround to show some plotting in terminals, in IPython terminal or IPython notebook, is a magic feature called pylab. Percentage sign, and percentage sign is always something like special feature in IPython, and percentage sign pylab. Okay, now we are using matplotlib backend with Mac OS X. If you use Linux, let's say if you use our school machine, you can do that too, and I can demonstrate that. So for example, if you want to SSH to our school machine. So here I SSH to our school machine and I IPython 2 and IPylab. It's going to take a while, but it uses a slightly different backend. Instead of Mac OS X, we use some GTK because this is running Linux. And then I can plot, and you don't need to say plot because this is it's already imported. So you just plot 1, 2, and it will show up. It will just, well, this is done remotely, right? It's through SSH, but it still shows up. Okay. This 1, 2 is because it's basically like x-axis is 0 and 1, and y-axis is 1 and 2. So the first point is 0, 1, and the second point is 1, 2. Okay, that's the way you understand it, right? So if you want to plot 1, 3, 2, that is interpreted as 0, 1 to 1, 3 to 2, 2. And let's see that. 0, 1 to 1, 3 to 2, 2. So the x-axis by default is always 0, 1, 2. Okay, and if you want to change, you can change it. So if I want to say the x-axis are 0, 5, and 3, let's just make it up, and it will be something different, right? 0, 5, and 3. So it's just being used to plot some data series, right? So if I have some experimental data or some real-time series or whatever, it comes with the x and y, and the way it works is the first point is 0, 1, the second point is 5, 3, the third point is 3, 2. So it's kind of a little bit awkward, but you hopefully get used to it. Okay, let's get back to our IPython notebook. Okay, now we'll be able to plot as is, and we don't need to say plt.plot, we just say like plot 1 to 4, for example. And this is 0, 1, 1, 2, and 2, 4, right? So again, now the x-axis is by default 0, 1, 2, blah, blah, blah. If you don't supply x, if you supply x, then it will plot something different. For example, if you supply well, let's say 10, 15, and 16. Doesn't matter. Just make it up. And it will just be, you know, like this. 10, 1, 15, 2, 16, 4, according to this statement. Okay, so that's our basic plotting tool. And now let's look at how do you generate these data points in random numbers. That's relatively easy. So you can just say np.random.rand. Well, by default, it just generates a random number between 0 and 1, and you can do it again. All right, it's always between 0 and 1. Now, if you want to generate a few numbers together, so if you would want to generate two numbers together, now it generates a 1D array, but with dimension 2, like a vector, two-dimensional vector, and these two numbers are both between 0 and 1. Now, if I want to generate, so that's basically like one little point, right? One little point. Now, if I want to generate 10 points together, so how do I do it? Well, I do it like this. 10, 2. Now I got 10 different points, so I got 2D array, right? A two-dimensional array or matrix or whatever, and it has 10 rows and 2 columns, right? So that's our data point. So that corresponds to something like this, and then we'll be able to draw it, right? And the way we want to draw it is again, so take the x-axis or the first column, and the second column as separate stuff. So, for example, we can say, let's take this guy as, so this is our data point, right? Now, if you want to see what is x-axis like this, and then you can take slicing. So if you slice the first data point, that is the first row, right? And the last data point, well, by the way, what do you think of -1? Well, -1 is the last row. It's again the last row. Now, what about you want to take the first column instead of the first row? How would you do that? You can do that in Python, but the way to do it in NumPy is colon, meaning the first row I take all rows, and the second, meaning dimension meaning column, I take the first column. Then I got just this vector, 1D array of 10 guys. So 0.9, 50, blah, 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 all the way to 0.27. And similarly, if I want to, the first one, right, I can get this, right, that corresponds to the second column. Right, that's how you do slicing. You can do slicing in a very, very flexible way with NumPy. So this all comes from MATLAB again. So if you are familiar with MATLAB, you will find it very, very intuitive and idiomatic. Now we want to plot this. So we plot x. If you just plot x, it'll be very different, right? So if you plot x, that's something completely different. Got this. What is this? This is two lines, two line segments, or two sets of line segments, right? The first one being this 49, 50, 49, 50, 44, 017, and blah blah blah. So this is the first series, and then this is the second series. It treats this matrix or 2D array as two separate series. But that's not what we wanted. We wanted to plot these points as these points. Okay, so the way to do it is to plot x0 and x1. So let's see. Let's clear our figure first, and then let's plot this, and then we'll add a square and let's say using blue squares. Okay, so these are our 10 data points. You can verify that. Okay, let's make it slightly smaller so you can see it. So the first one is 0.49.99. Where's that point? Okay, that's this point, 49.99. Okay, and what is this point? This point is about 48 or 49 and 0.3. Is there such a point? Yeah, that's 48 and 0.3. So that's this point, right? If you want to use a different color, you can use red, and then a different shape of the points, you can use diamond. And that's red diamonds, okay? Same positions, right? So that's how you generate random numbers and plot it. But these are different from this plot. This plot is, you know, according to a line, but with some noise or some variance. How do you do that? Well, it's very easy. We use x is, let's use x being vector and NP range 10. So again, what is x? X is basically 0 to 9. Now let's add upon it a very small noise, How would you do that? Well, I would do x plus np dot random dot rand. Let's say 10. So first of all, what is np dot random 10? That's 10 random numbers, and then if we add them up, that's going to be element-wise addition. Okay, so say x plus equal this, or you can let's demonstrate that first, right? So x is going to be something random, and let's just take the signal, which is a range of 10 plus np.random.rand 10. By the way, every time you got new random numbers, random numbers are freshly generated. Okay, so now this x, what is this x? This x is, very close to 0, 1, 2, 3, 4, 5, all the way to 10, all the way to 9, but with some noise. Okay, now let's plot that. So clear figure first and plot x. Okay, and let's use a plus sign and a cyan color. Okay, see that? So this is very similar to what we got here in the original plot, a reference plot, right? So this is our newly generated plot. It's very similar to this 0, 1 line, the y equals x line. So if we want to plot y equals x line, how do we do it? Well, we just say, well, we can do 0, 0, 0, 10, 0, 10. Okay, so this is the y equals x line. Again, it reads as 0, 0, 2, 10, 10. Okay, so it always reads that way. Okay, so this is our line. There is a little bit of a variance upon that, right? And, that's our randomly generated data points. And if we want to now fit a curve on it, we'll fit it. But we also can just erase this and regenerate new stuff. And then let's do this. What if I want to say, instead of always a positive variance, I want to sometimes positive, sometimes negative. So sometimes above the y equals x line, sometimes below that. So this way we can do minus 0.5. What does that mean? Well, okay, so first of all, we want to demonstrate something called broadcasting, which is also from, again, MATLAB. So if we have a range of 2 plus 3, let's say, that's a vector, right? And let's minus 1. what does it mean for a vector to minus a singular number, a scalar number? It doesn't work, right? It doesn't type check. But the answer is very simple. It just element-wise is as if this is broadcast to be 1, 1, 1, to be the same dimensionality as this vector. Then it's basically as if we are performing this operation, np dot array 1, 1, 1, right? Exactly the same. So NumPy, or MATLAB rather, automatically translates or interprets this minus operation of 1 being broadcast to all the dimensions so that it has the same or matching dimensionality as the previous number, or previous vector. Okay, so if you understand that, then if I say np dot what is it, random dot rand 10, all positive numbers between 0 and 1. If I just do a minus 0.5, it will be sometimes positive, sometimes negative, and between negative 0.5 to positive 0.5, the new range, right? Now if I just do something like this, np.range 10, sorry, arrange 10 plus this, then I'll get a points just sometimes above the y equals x line, sometimes below the y equals x line. And let's plot that with a blue plus. Okay, and then let's plot 0, 10, 0, 10. See, sometimes it's above, sometimes it's below, right? Now let's do finally the curve fitting, right? Okay, so how do you do curve fitting? A comma B equals, let me look it up, what I wrote here, my notes, okay, x, y, 3, okay, so here, what I want to do is, well, let's back up a little bit, and let's say x is np.arrange 10, and y is, this thing here, right? So you can write two different ways. You can write this way, or you can write the Pythonic way. The Pythonic way would be like xi plus, the way we write here, np.random.rand, a single random number for xi in x. If you write something like that, you got something very similar, but just in Python, not in NumPy, right? And you have to kind of, well, the right way to do it is you have to, let's say np.array, although you don't technically need to say it, but okay, so that's one way to do it, right? But we would rather use a kind of vectorized format, which is almost like a Pythonic way of saying that, but now it's like the MATLAB way of saying that. So arrange, or maybe just say x plus np.random.rand 10 numbers together and broadcast minus 5. Okay. Okay. Now let's plot x, y, and with a circle red. Say, okay. So we got another 10 points that's different from the previous 10 random points, right? And we can just do a lot of things like this, okay? Now let's, again, x.np.arrange 0 to 10, but instead of 10 points, I want, say, 100 points. So 0.1 being the interval, right? 0, 0.1, 0.2, blah, 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 blah. Okay, and then let y be x plus np.random.rand, how many? 100, I guess, minus 0.5. Okay, so I got y's, and then I plot x, y with a, let's use a square and a green square. Okay, so all these, wow, that's pretty big stuff. Let's clear it up and use rather smallish guys like plus, okay, these guys. But these are probably too many stuff. But that's fine. Let's plot it. Let's curve fit it. A, B is np.polyfit, np.polyfit x, y, and the polynomial degree is 3. Sorry, is 1 using a single line. Then what is A and B? Okay, A and B are these, and then we plot that plot. Okay, so plot x and then A times x plus B, that's this line, and using this line and a cyan color. Okay, that's the line we fitted. It's very, very close to y equals x, right? Now, of course, if we have less data, it will not be that perfect fit. Okay, let's do it again. So let's clear, and x is np.arrange 0, 10, and 0.5. Let's just generate 20 points instead of 100 points. Okay. Y is x plus np.random.rand 20 minus 0.5. Now let's plot x, y with a blue. Oh, this time we have some very, very large variance, very large error, but that's fine. Let's curve fit it. Okay, using polynomial degree of 1. That is using a straight line. What is AB? Okay, now plot x, A times x plus B with a single line using what color? Red color. Okay, yeah, got pretty good curve fitting, right? Now, what if we use 2 degrees of polymers of degree 2? So polyfit xy point of degree 2. The degree 2 you need 3 parameters, right? Now, how do you plot that quadratic curve? Well, we say a times x squared times b plus b times x plus c. Now let's use a different color just to make sure. A cyan. You see, it's very, very close. Why? Because you have a lot of data points, and that kind of, what is the word? Alleviates overfitting. Because otherwise, if you have only 5 data points, then it will be very, very overfitting. Well, if you really want to demonstrate overfitting, you can still do it. You can just use an even higher degree of polynomial, 3 degrees of polynomial cubic curve. Okay. Now you want to do a times x to the cubic, b times x to the square, c times x plus d. And let's use yet another color, green. See that? Right? Right. And you might notice that there's some zigzag here, but if we enlarge it, you might be able to see more zigzag. Yeah, zigzag. It's because we only plotted at the sample rate of 0.5 every 0.5 interval 0.5. So 0, 0.5, 1, 1.5, 2, blah blah blah. If we want to have a smoother curve, we still can do it. But let's try to erase that curve first, which is funny. How do you erase that? Well, with a white color. It's gone. You can still see the trace of it. You still see a little bit of trace, but it's really gone. Now let's use xx being np.arrange 0, 10 using very, very small intervals. So it has a lot more points of interval 0.01. And then let's same plot xx instead of x. x instead of x instead of x, and yeah, green color, you can see a much smoother curve, right? Much smoother curve. And you can imagine if I if I have the time, I can do the 9 polynomial fitting of 9, but let's just do one more fourth degree polynomial, and you can imagine how it goes. It goes like this. It's a little bit crazy. It's a little bit crazy, but it's a little bit crazy. Let's use a red color or blue color. Doesn't matter. You can see that. That start to overfit even more, right? Start to overfit even more. Okay, so this is the demonstration of linear regression using NumPy and Matplotlib.